So yesterday I was in Boston teaching, so that was why. This morning I was actually in my hotel room frantically trying to recover my slides because my video card seems to have died. And so every time I plug my laptop into an external projector, the entire laptop crashes. So I was transferring it onto my iPad and hoping this worked, so I apologize. That was not supposed to be the problem. Of all the problems out here, this was not the one that was supposed to happen. If this all completely falls apart during the talk and nothing is on this thing, I'll turn it into a Blackboard talk and hope for the best. Let me just reorganize this. Okay, so this is a good start. So today I'm going to talk about I'm going to follow up on what David said, which is that he was talking about general methods for using these sums of squares relaxations to get stronger algorithmic results. And today I'm going to talk about it in a specific context, which is finding. So as you can see, this is off to a great start. OK, so I'm going to work on trying to recover hidden sparsity through sums of squares relaxations. And OK, what's the high-level picture? The high-level picture is that I'm going to be talking sort of about two major goals. And they're going to kind of be both related and not related. The first goal is the algorithmic end result, which is finding denser sparse objects. So all the rage these days is sort of a general class of problems of the form, I give you some limited, noisy information, find something sparse. Right? So I have some sparse hidden object kind of buried in a bunch of noise. Somehow you have to find the object that's there. And there's a couple algorithms that match this template. I'll talk about them in a second. But the main question is just when can you do this? Obviously, if sparse is too weak, if sparse means, I don't know, missing one coordinate or something, you'll just never find it in any kind of case. It might not even be information theoretically possible. On the flip side, so the real question, I guess, is how sparse does the interesting thing you're looking for have to be? And how nicely unsparse do the ambient uninteresting things have to be? OK, so there's a whole bunch of questions that fit that mold, which I'll talk about on the next couple slides. And many of the results that are out there, and I'm going to have to, on the intro slides, make some overgeneralizations that are overgeneralizations, so bear with me on it. It's just to give the high-level picture. But the high-level picture is that a lot of the algorithms for solving the find something sparse type problems are some form or another of L1 minimization. You say, sparse things have a good L1 norm compared to not sparse things, minimize L1, hope something good happens. And in a pretty broad set of cases, the answer is yes, something does. So, but however, the how well does this work, like the how much sparser does the sparse thing have to do, in essentially all the applications where it's an L1 minimization thing that I know of, there's an answer of the form 1 over root n that I guess we've seen, I think you guys saw it while I was teaching yesterday in Boston, and it will come up a little bit later in the conference. And that 1 over root n is kind of an intrinsic feeling one, right? It's basically just, I look at L2 norms and L1 norms, and I ask when can I sort of when does the difference between L2 and L1 really pull out the sparse thing? It's when something is a lot sparser, where the a lot is some ratio of sparsity of 1 over root n. OK, so this 1 over root n you'll see occurring fairly frequently. And the main question we're going to ask is, can you ever do better, or is this really there? OK, the second question is, can we prove guarantees for the sum of squares or Lasserre hierarchy when the number of levels is small? And this one, there are some results, but surprisingly few. Roughly speaking, these hierarchies empirically and kind of from an intuitive standpoint seem very strong. And David gave some explanations of why they seem very strong in sort of a complexity setting. But broadly speaking, they seem like they really should do much better if I sort of replace level 2 with level 4. But there's really very few positive results for a number of levels that's less than some poly in n. So there's a bunch of positive results at square root of n levels or n levels, or maybe slightly lower. But if I wanted to get something at, say, 12 levels or log n levels, there's mainly negative results in the literature. And I guess the short version of that is that it's kind of hard to do algebraic geometry or semi-algebraic geometry if you're only allowed to look at low-degree polynomials. Even if you're asking low-degree questions, often you have to sort of rely on cancellations that happen at a much higher degree. And so the sort of second goal that we're going to shoot for in today's talk, in some very special cases, is just to get non-trivial provable guarantees for the Lasserre hierarchy when the number of levels is some very small number, not root n, not n, but 4 or 8 or log n. OK, so those are our two goals. And as you may have guessed, we're going to combine the two goals. And so the goal for today's talk is going to talk about a couple of cases, really focusing on one, where the second goal lets you solve the first. So what I'm going to do is use Lasserre hierarchy to solve some sparsity type questions, and in doing so, outperform what seems like the intrinsic limit 1 over root n that you're stuck with on L1. OK, and again, I'm going to sort of, what I want to do is first very quickly just kind of run through the scope of what these results look like, and then I'm going to pick one of them and actually do it with equations. So I'm going to sort of do sort of the fluffy high level, these are all the problems one could think of that match my template, and then I'm actually going to do one and kind of just illustrate in detail roughly how this technique works. So, OK, the first problem, which is the one I won't do in detail of the two main problems, is dictionary learning and sparse, which is also known as sparse coding. And this one has come up a lot lately. And the high-level picture of the question is I give you a bunch of vectors, a1 through am and rn, and I give you samples from some distribution. So you get examples of the form the sum of w sub I, a to the ith vector, where you tend to get sparse combinations. So each of the wi's is from some distribution where most of the time it's 0. So the probability that an individual one of them is non-zero is something much less than 1. And our goal is from this to recover the dictionary. So the idea is that I'm giving you a bunch of samples from some distribution, and I promise you that it's sparse in some basis, and you want to find the basis in which it's sparse. So this is a very well-studied question. It sort of came up in machine learning back in the 90s to find the right representation of observed data. So the moral picture here was I give you, that sparsity illustrates you sort of looking in the right representation of something. I give you a bunch of numbers, and I want to say what is the representation that illustrates their structure. I lifted from Boas this convenient, pretty picture. And this has a lot of work, because it's been used a lot in machine learning, vision, and neuroscience. And the rigorous results that were out there were under various combinations of assumptions, a bunch of them, but largely, and again, this is the slight overgeneralization. There was a simultaneous paper that was under slightly stronger conditions in some parameters and not others, et cetera. But largely speaking, the existing rigorous results were 1 over root n for the sparsity, the mu, which was the probability that one of the w's was non-zero. So this is one of the 1 over root n's I've been talking about. And this says that if I gave you these random samples, the distribution they're from, it should be that the vectors that are proposed to be sparse are actually really sparse. They're sparse in the sense that all but a 1 over root n fraction of the entries are 0 for these sparse vectors. And then somehow, hopefully, that means that the signal really jumps out at you. OK, so what we can show, and it's going to be using techniques that are related to what the second problem I'll talk about, but somewhat different and are in a different paper, is we'll show actually that under, so in all of these cases, once you need some assumptions, right? Like, so for example, if I were to tell you that you had so much noise or so sort of minimal sparsity that you just kind of get sparse vectors anyway, just by chance, then it's really hard to find things. Like you don't want to say fully independent samples from a general distribution, right? Like if these samples were if the w's were completely independent, you'd have some probabilistic guarantees you could exploit. You want to minimize the assumptions that you have, but you do need some that roughly say that the stuff that isn't supposed to be sparse, like that an arbitrary vector doesn't look too strongly like your sparse vectors that you're finding. So you need some mild assumptions that are really there from the identifiability standpoint. And under those, even in sort of non-independent coordinate cases with over-complete bases, so here, note the AIs could be a basis, or they could be much more than a basis. And in applications, it's very easy to motivate that you'd want to have many more dictionary vectors than you have dimensions. And even in those cases, we show under some mild assumptions that you can actually recover. Yeah.
In the real world, how sparse do you want to be able to handle? Like, if you're actually doing vision with this.
I think that. OK, so there's a couple real world apologies I was going to make shortly. In the real world, the how sparse is as sparse as you can. The apology I was going to make is that right now the algorithms that we have for this problem, the running times are not quite in the real world yet. They're n to a fairly large number, but in the real world part of it, really whatever you can find, right? Like,
I think it's used in very different applications, so it's kind of also the sparsity level varies pretty widely.
No, but one answer is that the real-world algorithm they use, this gradient descent on the non-convex function, stops working after 1 over root.
Right. Yeah, so somehow the limitation is an intrinsic one to the heuristics even. And so the 1 over root n is a limit of what the algorithm would try to do, and so you're not going to use it in the real. So it's what they use it for in the real world is where their algorithm ever works. Does that make sense?
I guess one quibble though is that it's also, if you make enough independent solutions like ICA, right?
Yes.
And there's no.
Right there, that was my sort of brushed under the rug, even when non-independent under weak assumptions. So that was what I was referring to when I said that you can, if you assume that everything is sufficiently independent, then you can kind of probabilistically understand exactly what's going to happen and pull out the answer, which is what ICA lets you do. But here, sort of the win in this, and also in a paper that you guys wrote, was that you can do this under much weaker assumptions on how independent the coordinates are. Because I think independence is really a stretch, right? Like I think independence is a pretty strong assumption to hope for.
No, but people claim that for ICA, 4-wise independence is enough and things like that.
Let me answer that offline just because
Independent component analysis.
I don't want to get too hung up on this slide, so let me answer that either afterwards or offline just to kind of push forward. But I would slightly dispute at least that strong an assertion. But anyway, let me come back to that at the end just because I don't want to dwell on my intro and not get to the technical part. But I'm happy to answer questions about that after. Okay, so this is the first one. The second one, which is the one that I'll actually work out in detail, is what we'll call planted sparse recovery. And it's a fairly similar one intuitively, but with different parameters, numbers, and goals. And so the idea is just I give you some random subspace. And here for now, let's actually go with this is non-trivial even when the random really means random. So for today's talk, we're going to not worry about, we're going to make random as nice as we can and just make it really legitimately a uniformly random subspace from the Haar measure. And the goal is I'm going to take one of these random subspaces, which we'll pick in regimes where you tend not to have sparse vectors just by chance, and then we'll just plant a sparse one in it. And so the setup is I plant a sparse vector into a random subspace, and you want to recover it. OK, so let me just say that a little more precisely. So the setup, because this is what I'm actually going to do with math. So the setup is I give you an arbitrary basis of some n-dimensional subspace, d-dimensional subspace of Rn. And so think of it as I have the span of some v prime with some fixed vector f0, where v prime is a d-dimensional subspace, and it's random. And we're going to think of this as the span of IID Gaussians. And then we'll say that f0 is our planted sparse vector. So it's some arbitrary sparse vector. And mu will be the sparsity. So by the mu sparse vector, what I'll mean is just that if I say mu sparse, I'll just mean that the size of the support is mu times the total number of coordinates. So mu equals 1 over root n is the sort of is the thing I was referring to on the previous slide, and kind of now we're talking hopefully better than that. OK, and so the goal is going to be to find a vector that, quote, recovers the planted sparse vector. OK, so let me just briefly mention what the goal I'm going to solve is, and whether or not you really need such a strong goal is a moral question, but we can get it, so we might as well prove the strong result. So for today's talk, I want you to think about the goal as exact recovery. So the goal is going to be that, like, really, this is an actually sparse vector planted into a random subspace. There, at least information theoretically, should only be one. And so we're going to try to really recover it. We're not going to get a close vector. We're going to get the vector where the approximate really just means sort of to high numerical precision. And so think of it as you want running time that's log 1 over epsilon.
Does it matter how the non-zero coordinates in F0 are selected?
No.
Non-zero doesn't matter.
Not for this, no. So, right, yeah. So f0 is arbitrary, it's just that v is nice. Or v prime, rather, is nice. OK, and so note that f0 is not required to be random. I could have that on my slide. And in fact, you can even actually randomly choose v prime first, and then adaptively, adversarially choose it. So that's going to be our problem, and it shows up as a primitive in a bunch of cases. Before I talk about how to do that, I just want to mention briefly a couple other problems. The other problems that sort of are solvable by related techniques to what we're talking about that I'm not going to really go into, and I put briefly as my excuse for just, I want to mention they exist, but I don't really want to define them technically, because some of them require fair digression to do so. But the problems where the same techniques actually let you break some existing barrier. One of them is noisy tensor decomposition. So broadly speaking, I give you some tensor, and I want to find an approximate decomposition of it into a bunch of rank 1 tensors. assuming that such a thing exists. And so the idea is that we're going to be given a tensor that is close to it, but in a fairly weak sense of close. So the problem is just I give you noisy access to a tensor that's proposed to have some non-trivially low rank representation, and I give you sort of noisy answers. So it's close in the spectral norm, which means as like considered by a matrix, if you consider the tensor as a matrix, basically, or as a function on the sphere. And you can think of what this lets you do that you couldn't do with the sort of existing L1 motivated techniques, is it lets you handle a much greater level of noise at the expense of a fair amount more computation. So rather than giving a practical fast algorithm that solves it where you have inverse polynomial noise, so you're basically just solving a fairly close to exact example of your tensor, we're going to solve it with either constant noise or very close to constant noise, depending whether you want a polynomial or quasi-polynomial algorithm. And actually, the result will be that under very mild restrictions that just are necessary to make the problem make sense, we can actually do this even when there's a huge amount of noise, when the noise is constant instead of inverse polynomial. And kind of the relevant, interesting fact about that is that this is a regime where you no longer get, like where if you do these local gradient heuristic procedures, this is enough noise. The 1 over poly noise is what you need so that actually you expect the local minima of the nearby thing that you're minimizing to have something to do with the local minima of the original thing. And this is outside of that regime. So the interesting fact here is that this is something where the local minima have nothing to do with each other. OK, so the next one I want to mention, which ties into what David talked about, was sparse vectors in arbitrary subspaces. And this one is, I'd say, a substantially technical, harder result than the one I'm talking about today, which is why I'm not talking about it today. But I find it kind of surprising. And so the setup was previously I told you I'll give you a random super nice subspace, find a sparse vector in it. And we can do that under very good, very, very weak assumptions on the sparse vector, but very strong assumptions on the randomness, right? So sparse can mean pretty dense, but random means super nice subspace. Here, we're going to solve appropriately formulated variant for a worst case subspace, but with a weaker guarantee. And so what the assertion is, and this actually has small set expansion implications, which are not enough to, well, David co-authored the paper, so therefore didn't refute anything David said. But it's something where they're stronger than, they are non-trivial implications. And so the setup is, you have to be a little careful how to formulate it, but roughly the question that this lets us answer is I give you a d-dimensional subspace that either contains or almost contains, depending on your choice, either way, the characteristic function of a sparse vector, and we're going to recover a vector that is not as sparse, but non-trivially sparse. And so ignore the word analytic sparsity for a second. Let's just pretend I wrote sparsity. What this says is that if you have sparsity mu in an arbitrary adversarial subspace, you can find a vector with sparsity mu times d to the 1/3. Even root d is not super trivial. It's not super hard, but it's OK, so what is analytic sparsity? Analytic
sparsity also, still it's NP hard to determine whether a set of points are in general position or not, right?
Right. So
it tells you a very strong statement about, I can find a vector which is, k sparse but not k minus 1 sparse if it exists, right?
Yes.
They'll both be analytically sparse.
Yes. So let me define analytic sparse. But yeah. So analytically sparse is a relaxed There's one, probably if I took a somewhat nice arbitrary subspace, it may have no exactly sparse vectors in it. So if I were to find, any kind of exact sparsity guarantee, I might be asking you to just find the vector, right? Like I could just give you, but somehow you want something a little bit more geometric. And so analytic sparsity just says that if you look at norms of the vector, you look at the ratio of the p norm to the q norm for some of your favorite p and q, then in our case, let's say 4 and 2, then the ratio behaves as if the vector were whatever that sparsity is. So think of it as, if I give you if I gave you a vector that wasn't exactly sparse but had a very high dot product with a sparse vector, that's more of the kind of thing one would hope to find. And if you don't have that sort of assumption, I think you are quickly lapsing into the NP hard question range, just because there might just be exactly one sparse vector that's even vaguely sparse. So this is, I think, the right way to formulate a relaxed version of this problem where the answer isn't obviously NP hard. And then the question that we're solving here is for an arbitrary subspace with a sparse vector in it, we're going to find a fairly sparse vector. Okay. So now let me. Also I wrote this one. I really didn't want to try to explain this one because Aram's going to do a much better job at it later. So I'm just going to say also some problems in quantum information with related techniques and push that forward to Aram later in the week. Okay, so that was the high-level picture of what we can do. And broadly speaking, the upshot was things that have sparser or noisier answers than you would expect from just doing L1 minimization. Okay, so let me now tell you I'm going to say recall from previous talk and remind you what David said in the last 5 minutes, because that's the main tool. And then I'm going to run through the algorithm for the planted sparse vector thing in the random subspace. And I think it illustrates a couple nice features. Okay, so let me remind you what David told you right at the end of last talk about the high-level picture for the Lasserre hierarchy. And I'm going to do this fairly quickly because I think a lot of the people here could do it at least as well as I could. But if I do it too quickly, do stop me. Because since David just said it this morning, I'm going to breeze through this, but possibly at a unsustainably fast rate. If so, stop me and ask questions. Okay, so the basic goal that one addresses with these polynomial hierarchies is some polynomial optimization problem. So think of it as I give you some program P that's going to be maximize some polynomial P of X over, think of P as being a low degree polynomial, where if all those P's are low degree, this is still NP hard. And think of the goal as I want to maximize P of X subject to a bunch of polynomial constraints.
Do you not want X on the hypercube instead of Rm? The maximization question isn't the domain.
Oh, so you could impose that with the P's. So for example, if you want it on the hypercube, you just say that x sub I squared equals 1. So x sub I squared minus 1 equals 0. So the reason I wrote it this way is that sometimes you might want the sphere, for example. So it's nicer to keep things general. Usually, most of the cases I know of, this will either be constraints that will put you on the sphere or the cube. But not always. Okay, so the idea that, David, yeah?
What about inequality constraint? Can you order?
I kept them out because it will not show up in anything I'm going to do today. The Lasserre hierarchy does say things about inequality constraints. I'm not using them and thus didn't want the additional notation. So today I'm really going to think of it as equality, but there are ways to write things that are just slightly more technical that will deal with inequalities, and I'm trying to dodge that point just to not deal with it. Okay, so this is our goal, and the relaxation says it. So as David said, you get sort of a relaxation, and you're going to have a primal and a dual, and maybe I'll put them both up just so you can see them. And let me start with the dual. The idea that the dual is I want to convince you of a bound on this polynomial. So I want to convince you that there is no possible point subject to your constraints, so that this polynomial is bigger than some cutoff. And so the idea is that I do that by producing a proof, and the proof system that David was talking about is the one I'll use, which is that I give you a sum of squares proof. So that means that I give you a bunch of polynomials, and basically I'm working with the assertion that if I give you real numbers, if I square them, they become positive. And so if I want to prove that P is less than V, what I'll do is I'll basically say if I add something that's supposed to be 0, then I'm adding 0 to the objective function. If I add something that's supposed to be positive, I'm only making it bigger. So if I can prove that my objective function times something that's positive, so if I take objective function minus some guess, multiply it by something strictly positive, and then show that that thing is positive, then I've got a proof of a bound, right? So, just all this is doing is taking the axioms that the square of something is positive and 0 is 0, and then seeing what you can deduce from that, only using polynomials of whatever degree you're looking at. And then the dual thing that David talked about was the pseudo-expectation idea. And so the idea is that the right dual object to these sum of squares proofs, meaning that if you were to take the actual search for sum of squares proofs, it turns out to be a semi-definite program, and if you write down its dual, the objects that come up are sort of things that are pretending to be probability distributions. And what that means is that actually what they give you is the alleged expected values of polynomials up to some degree d. So the primal objects that we'll deal with say, I'm going to try to solve this program P, which is I want to maximize a polynomial over some set. And then what we're going to do is think about it as, there might be many solutions. So the right question, if I'm doing anything convex, isn't one solution. It's any convex combination of solutions. So we're going to think of the goal as being to try to describe any probability distribution over optimal solutions, which of course we can't do. So instead what we're going to do is describe numbers that look like they could be the moments of that probability distribution. And so the notation I'll use following David is that I'll write an e tilde just to mean sort of what the semi-definite program proposes the answer should be. And so the setup here is that a pseudo-expectation, which is a primal solution to this relaxation, is a linear operator on polynomials of degree less than or equal to d that satisfies the constraints that moments should satisfy. And so what are those constraints? One of them is that the expected value of 1 is 1. The other is linearity of expectation. And the last one is that the expected value of the square of anything is supposed to be non-negative. So it turns out that you can write down, if you wrote everything down carefully, these are the constraints that characterize primal solutions to the Lasserre hierarchy. So the picture that we're supposed to have here is that I give you this optimization problem. We're then going to solve what turns out to be a low degree semi-definite program. So if I give you the degree d relaxation, there's like n to the o of d monomials. And so what you end up with is a semi-definite program of size n to the o of d, which you can solve in n to the o of d time. And so what you get out of your relaxation is you get a bunch of numbers on the primal that propose to be the expected values of polynomials. So it proposes to give you a linear map that computes expectations, and it's subject to the sort of easily enforceable constraints that these numbers should obey. And then the dual objects are proofs that those distributions can't exist. And what that means is sum of squares proof. And the hope here is that somehow given these, we're going to be able to, so this gives us a way of taking any program and relaxing it. And then the question is just, does this relaxation accomplish anything? Meaning, does this, can we say anything about how good an answer this relaxation gives compared to the actual answer to the original program? Are there any questions? I did that sort of.
Where do the PIs come in the primal?
Oh, that's a very good point. They should have expected square 0. So they should have, so the expected, did I drop that? Oh, okay, so that is a fair, I guess this was a generic pseudo expectation, right? So the constraint that pi equals 0, what that shows up as, thank you, it shows up as the expected value of p times anything is 0. So e of p of x is 0, e of p of x times 7x cubed minus 4x squared over 2 is 0, right? Any polynomial times 0 is supposed to have expected value 0. Other questions? Okay, so now let me kind of remind you the picture, and then after this I will stop reminding you and actually start doing theorems. And the last reminder I want to give you is the picture that David was describing. So the picture is the following. Our approach here is going to try to take this sort of moral description of moments and proofs and use it to actually guide our rounding algorithm. So the idea is that pseudo expectation is supposed to look like the expected value of polynomials, and if I actually it turns out we can actually solve the problem of finding pseudo expectations. They just might not actually correspond to legitimate expected values, and so. What we're going to try to do is lift our proofs about real random variables to proofs about pseudo expectations. And so kind of the high-level picture of what our goal of how all these algorithms are going to work is as follows. We're basically first going to say, okay, you know what? Pretend that I gave you something you completely can't compute, which is pretend I actually said I'm going to take all the actual optimal solutions to your problem and give you a probability distribution over them. So I'm going to give you a probability distribution distributed over optimal solutions. So if you could just find one of them, you'd be completely done. I guess it's finding hay in a haystack. And the idea is that I'm not going to give you the distribution as an oracle that samples from it, because that would be the whole problem. Instead, what I'm going to do is I'm just going to give you the moments of the distribution. And what we're going to try to do is we're going to try to say if I gave you an actual distribution, and I just gave you its first d moments, how could you recover a fairly good solution to the original problem? And then what we're going to do is we're going to say, here's how you would do it for an actual probability distribution. Here's how you prove that it works. And then we're going to take the proof that this thing that worked for exact, actual, legitimate probability distributions worked. And we're going to figure out if we can actually write that proof only using low-degree polynomials. And so, if we can show that that I could take sort of an actual solution and then write the proof of correctness only using moments of low-degree polynomials, then that will actually give us a way, that will actually depending on how strongly we state this, either formally or morally suggest how to find an actual rounding algorithm. Right, so the idea is we're going to think, so that's the kind of intuitive picture we're going to work with. And the rest of today, I'm going to give a worked example of this approach for planted sparse vectors, which I did because I think it's a nice, clean one. It's probably the technically easiest of the bunch, which is why I picked it. And it also illustrates a couple key points that I think are worth noting. And I'm going to mention them before I talk about them so that they kind of stick out when I talk about them. But there's a certain set of frequently occurring facts or pieces that seem to show up in a lot of these applications that I just want to mention. One was, as David said, these things sort of all seem to hinge upon the question, what can we prove with low-degree proofs, right? So in all of these cases, really we're going to be looking at, the setup we're going to look at is just, could I convince you there was no good solution only using low degree? The next thing that I want to point out is that we have to use the problem structure. And this is a very strongly true statement that's kind of important, which is that if I were to only think of these optimization problems that we're solving as optimizing a degree d polynomial over the cube or a semi-algebraic set or whatever I want, all of these things would need polynomial degree, and provably so. So later, I think there'll be some talks about giving, under very general settings, how to get strong convergence results at like degrees that are poly in n. And those are necessary if you're doing arbitrary optimization. So somehow what we have to do is design an algorithm that exploits problem structure to just say that we don't need to just treat this as general polynomials. Next thing is that our rounding is directly motivated by our moment intuition. You'll see a concentration of measure tends to come up a lot. And so do multiple norms. And I guess I kind of want to give you what I think are the two motivating questions for any algorithm that looks like this. And I claim that these two things are at least necessary if you're going to solve any kind of optimization problem. One of them is, suppose I actually just gave you the moments of a whole bunch of solutions. How could you isolate one of them, or one fairly good solution? I guess if you have any algorithm that solves the problem, clearly it could solve this problem by ignoring the information you're given. So this seems weaker, right? I'm giving you access to additional information, which is just a bunch of actual moments of actual solutions. How can you pull one out? And kind of the other one, which I think is maybe more technically motivational, is if I actually if I lied to you, and I just gave you a planted sparse vector problem where there was no vector, how would you figure out that I'm lying? And we'll see that in some sense these two questions will motivate the structure of the algorithms. So how would you tell if I just didn't plan a vector at all? So very briefly, let me remind you sort of what kind of the L1 algorithms looked like, and then it'll motivate how we don't do them. So the idea is that they were motivated by L1 minimization. And so just the idea here is that we're trying to I give you a random subspace and a very sparse vector. And we're going to look at what properties are sort of true of typical vectors and what properties are true of our sparse vector, and hope to find one that lets us separate the two. And this is a sort of caricatured picture of a typical vector. Its coordinates, put theta or theta tildes around everything I write here, of course. It's just to give you kind of the broad scale. A typical unit vector. And I should say, by the way, throughout today, I'm going to be using expected value norms. So think of it as, it's a normalization that makes this very convenient. So for example, the way I wrote it here, I'm going to write that the one norm of this is 1. Think of it as the expected value of whatever polynomial you're looking at if you pick a random coordinate. That's the scaling I'll use. So and so this is a unit vector, not that over root n. And so a typical unit vector, all of its coordinates are roughly the same size. Its one norm is 1. Its infinity norm is 1. Its ratio of 1 and infinity norms is 1. Whereas for a very sparse vector, it kind of looks like this, right? It's got a bunch of coordinates. The sort of least sparse vector is going to be that they're all kind of the same size. So you have a bunch of coordinates.
So the L2 is 1 in root n?
Yes, it's 1.
1.
It's 1? How? So
It's
Expected value over.
okay.
Right, so the idea is I'll define.
Between 1 and infinity are also 1.
Right, so it's the expected value of negative 1 squared, or 1 squared over. It's just a nice normalization later. Okay, and so now a typical sparse vector, the point is just that now you're going to really see a difference between the 1 and infinity norms, right? If I were to take a typical sparse vector, then its one norm, you'll be adding up a bunch of 1 over root mu's, and you'll get something like root mu, whereas its biggest coordinate is 1 over root mu. And so instead of getting a ratio of 1, you'll get a ratio of mu, which is much smaller. And so this says that if you do the right minimization problem, you can hope to find the sparse vector, right? So what it says is that we're going to try to find our sparse vector by computing the best ratio of f1 to f infinity. And that may not be obviously a problem you can solve, but it actually turns out to be an LP, and a very easy one. Because the idea is that what you'll do is note that this is the same problem. I'll minimize the 1 norm where I'll guess which is the biggest coordinate. So for each of the possible largest coordinates, I'll solve the problem of minimizing the 1 norm. And then whichever one of those will be the one that comes from the 1 to infinity norm. And so what you get is that you can solve this nice LP, and you can end up with the vector that actually does exactly minimize the 1 versus infinity norm. And then the question is how well this works. So there's my notation note that I believe was earlier in the slide when it was on my laptop. But that was my expectation norm thing that I just said. OK, and so now the idea is we're going to try to find f0 by computing this. And if you look at how sparse f0 has to be, our caricatured vectors actually kind of tell us the answer, right? Like, we need to be able to, the 1 over root d, where d is the dimension down here, just comes from this exact assertion, right? Like, we just need to know that when I actually look at the sort of typical versus sparse. OK, so now I need to tell you one more thing, which is why you might say this seems like it works for all mu. And now what we have to do is we have to ask the question, essentially, how bad a solution do we expect to be in a random subspace? So the previous papers, in a second I'll tell you exactly what the answer is. OK, so the previous papers showed that what you can do with this approach is actually get O tilde of 1 over root d. And I claim that this is actually tight, and I think they also claimed that it was tight. And so the first question I want to ask before I say can we do better algorithmically is, are they just analyzing it wrong? This is when I said that I think there's an intrinsic reason why these things can't do better. This is the intrinsic reason, is that it's not just that the analysis is wrong, it's that you actually expect a random subspace when you have any mu that's worse than 1 over root d. You actually expect a random subspace to have a vector that you expect that no longer will your planted vector be the solution to the problem.
I think there is a theorem that for every subspace of dimension d, there is a...
That's true, actually, yeah. Right, so actually, Boss makes a good point. It's not a random subspace. It's a random subspace is your best case scenario, actually. It's all subspaces. And in particular, a random one. And likely, I guess I mean with probability, very likely. OK, good. So the proof I'm giving will show likely. The real proof will give exactly. But this one's simpler to draw a caricature of. And also, I might have forgotten this late last night. OK, so my assertion is that a random subspace is, in fact, likely to have some vector where the ratio is O of 1 over root d, in which case you really won't find the correct answer. Right?
Well, disagree.
It's true, right? But this one's got a nice, pretty picture, which is why I did it. I just want to give the argument for it, because it comes up as a good counterexample to a lot of things. And I've told enough grad students this argument that I feel like I should put it on a slide. And so let me convince you of why random subspaces tend, in fact, with very, very high probability, to have vectors with this bad ratio. Oh, actually, no, the 1 to infinity, I'm not sure I buy this anymore. The 2 and... I think you're telling the truth for 2 versus...
I guess we should work it out. I thought it's 2 for every subspace, but I guess we should work it out.
Boaz may or may not be telling you the truth, but this one is definitely true. So anyway, the idea is we're going to think of our subspace as a span of a bunch of random vectors, right? And then I'm just going to construct for you a vector that has a very big, very bad ratio of norms. And so the idea is I want to construct a vector in a random subspace where some coordinate is much bigger than all the others. And it turns out there's and again, the reason I write this is that actually I've had multiple times in my life where people have suggested conjectures where this breaks them. So it's just a good example to know of. And so how do you get it? So the idea is that I'm actually going to by hand construct it. And so what I'll do is I get my random subspace as a span of a bunch of Gaussians, independent Gaussians. And what I'll do is I'll just add them up. But I'm going to add them up with a carefully chosen sign so that I get some coordinate to be really big. Let's say what's the dumbest way to do this? I'm going to make the first coordinate really big. And the way I'll make the first coordinate really big is I'll just make all the signs so that the first coordinate is positive. Right? right? And that will be a vector in my subspace. So I'm just going to take each of the vectors that I get as my random things that span the space, and I'll either add it or subtract it so that the first coordinates add up and all the other coordinates cancel, right? So what you get is vectors that look like a bunch of plus minus ones. The first coordinates are all plus ones. All the others are plus or minus ones. And so your first coordinate tends to be about root d times all the other coordinates. And so what you end up with here is just in a random subspace, you actually expect to have a vector where the first coordinate is root d times all the others. And that is the construction that shows that we actually have something tight. So here we have something with a 1 versus infinity norm that's about 1 over root d. OK, so now let me tell you what we'll do to do better. If my, oh, there we go. My iPad is struggling with my slides. So OK, we're going to today focus on the case where d is O of root n. So remember, there's two parameters here. There's the dimension of the subspace, and there's the sparsity. Here, we're going to look at lower dimensional subspaces, but much denser sparsity. And the O of 1 over root n is mainly to keep things clean. We can soften this a little bit. OK, so the main theorem I'm going to prove for the remainder of the time I have is that you actually can find this planted sparse vector even when mu is a constant. So that means in a root n dimensional subspace, even if a tenth of the coordinates are non-zero, that's you can as opposed to 1 over root n, you can actually find it. And the idea is just we're going to look at better norms. So instead of comparing 2 to 4, instead of comparing 1 to infinity, we're going to compare 2 to 4.
What can you say about d is linear?
Less. It's a harder problem for various reasons. So here, the algorithm that I'm giving really, so there is a result that will say that essentially if you want to say almost linear, then what you can do is get an algorithm that will have, you want to say almost linear, instead of being linear, it's n to the 1 minus epsilon. And I believe that what I'm talking about, although I should check it, will give a slower algorithm for an improvement for n to the 1 minus epsilon, where the running time will blow up pretty badly with epsilon. This one gives a non-trivial improvement up to like n to the 2/3.
I'm not sure about it. Like we definitely can improve until d is n to the 2/3.
Well, n to the 2/3, this algorithm works, but if you use like the 2 to the 2 plus epsilon norm, we haven't checked that. So that's a assertion I should not be making on videotape. I would guess that, so this algorithm gives better results up to n to the 2/3 dimensions. I strongly suspect, but have not checked, that if you wanted n to the 7/8, that you could do it with using, instead of the 2 to 4 norm, the 2 to the 2.1 norm. But that would come at the expense of having to do much higher degree proofs, so you get a running time.
It would be an interesting thing to prove.
That would be sorry, let me phrase that as a suggestion for an open question, so that I am not lying too badly in video. But let me suggest that the way you might want to analyze it is by looking at the 2 to 2 plus epsilon norm, writing that as a polynomial, relaxing it to a higher degree, let's say a relaxation, and then kind of running through this proof.
Certificates for non-sparsity at n to the 2/3, because there's an existing argument for that breakdown at n to the 1/2.
One more time?
What are the, like, you need some certificate, some SO certificate that a random subspace doesn't contain a sparse vector.
Right, so I'm going to give that right here. So after the 2 to 4 thing.
Like, how do you do that at n to the 2/3? Doesn't that break, that argument breaks down at n to the 1/2, right?
So the argument I'm about to give here is going to actually run up to n to the 2/3 with a trade-off in the sparsity. So you get constant sparsity at n to the 1/2, and you get better than 1 over root n at n to the 2/3. And then what I was guessing / proposing as a research problem was that you can get better if you make more aggressive norm ratios, that you can still do this. OK, so the first point is just imagining that we had magical computational powers and could actually answer certain questions that are NP hard. Let me first just convince you that we'd at least not get fooled by the things that trick L1 versus L infinity. So my claim was these vectors I constructed, these sort of adding with positive signs type things, are at least up to constants sort of the right thing to check for random subspaces for most questions about norms. Right? Like if I want to ask what is the worst case ratio of norms and I don't care about small factors, these are pretty close to the right answer. And so let's just check whether they break what happens with them. And this is where you'll see the bounds kick in. This is where my assertions about root n show up, is that if you now look at the 2 versus 4 norms of these vectors, you'll see they're not fooled by these bad examples. So a typical unit vector, we have 1, 1, 1 for the 2 to 4 norm because it's all 1s. Here you'll see that the 2 norm now is 1 and the 4 norm is like mu to the -1/4. if you write it out. And so what you'll see is that, because you're just looking at different ratios of norms, and the point is now this sort of a typical mu sparse vector here, you get a n to the 1/4. And so now if I were to look at these bad constructed vectors, what will happen is that we'll get a vector with this first coordinate being substantially bigger than the others. But if I'm raising it just to the 4th power and not looking at an infinity norm, then it's not going to get big enough to beat all the others in the 4 norm, right? And so what we'll see is that these vectors actually have 2 to 4 norm that's still constant, as opposed to the mu to 1/4 that you get from a mu sparse vector. So the sort of motivating mathematical fact that makes this go is that the vectors that actually show that this L1 versus infinity norm thing were tight, they actually are not a problem if I could optimize the 2 to 4 norm. That these bad vectors that broke our previous algorithm, they really legitimately don't break. They're not a good example of there being a bad ratio of 2 versus 4 norms. Right, so the 2 to 4 norm minimization that I'm about to propose will at least detect these vectors as not being problematic. Okay, so. Question?
Yeah. I saw. I'm cheating. I saw a talk by Story and Aaron's, and I'm stealing Aaron Sidford's example. But he says even if you take 2 of the coordinates and set them to be large, like in some trivial way, instead of going all the way to 4 norm, it's not easy to add up vectors to make 2 of the coordinates have large infinity norm.
Right. So
that also breaks the counterexample. I'm just saying maybe that's another way to break that.
Yeah. So I don't know how to. Well, I mean that's a harder one to then break all examples with, right? Like this one is a nice polynomial. I guess the nice thing about it is that 2 versus 4 norm. You can break individual counterexamples.
Have a large L infinity norm is still a linear program, right?
Right. But how large would you make it? I mean, you'd have to do a larger and larger linear program to make fewer and fewer. Like, you can.
But
it's not clear to me that you couldn't get omega of.
You get like a 1 over root.
You couldn't get 2 coordinates that are like
1 over.
Omega of square would be larger than the other ones, because you would use like half of your basis vectors you would use to bias the first coordinates, and the second half of you would use to bias the second coordinate, and you wouldn't win too much because
Right, so what you get is
the scaling here is really.
Well, I mean, I think the scaling is that what you get is that you can. I thought 2 was supposed to be a proverbial 2, not an exact 2. So in the general sense of constantly many, what you get is that as the number grows. Oh, good. Oh, that was all you wanted? Okay, cool. Thanks. But anyway, more generally, it actually is numerically interesting that what you could do is you could try to make a bunch of them small. And what roughly you do is the same argument I just did, but replace with projection onto a random subspace. And so you'll get that their maxes probably will fall off linear or square root wise with the size of the number of coordinates. Maybe linearly. So that would be a harder one.
Asymptotically break 1 over root n until you go to
something that'd be a very big, which would be a bigger linear program.
Extend.
Yeah, but then you'd have to just have very large linear programs, right? Like this is going to be a very small. This is going to be an n to the 4th size program as opposed to an n to the something bigger than a constant. Okay, so now let's see how to turn this into a general algorithm, and the problem, other than the hourglass that's appearing on my screen, is, okay, so more generally, let's suppose we could solve a problem that we cannot solve because it's NP hard. The problem we're going to not solve, but hope to solve, is maximizing the 4 norm subject to being on the unit ball. So really we're trying to get the best ratio of 2 versus 4. And let's suppose the support of f is contained in some set S of size mu n. So let's just look at what happens with the norms, and I'm going to convince you that if we could solve this problem, we could at least in that case recover what we're looking for. So again, this is an NP-hard problem. But if we just kind of do simple algebra with norms, what do we get? I'm going to do this a little quickly because I'm running a little slow. But what we get is we just get that. So if we remember, we're not using fake expectations or anything here. We're doing legitimate actual probability. And we can use the fact, the fact that the expected value of f to the 4th is at least the square, the expected value of the square squared. And then kind of playing with inequalities as you go through this, what do you end up with? You end up with that the 4 norm to the 4th is at least mu times the 2 norm to the 4th, just by using Cauchy-Schwarz. And so what you end up with, that says, is...
The last,
oh, maybe my mu...
Yeah, 1 over mu, I think. It's,
oh, I'm sorry, yeah, right, so mu squared and a mu, yeah, so it's... Thanks, right, so the only typo was this last equality, right, and that was right, good. 1 over mu, or else that would have been very surprising for our algorithm.
I mean, it's true, but not very
yes, right. Okay, so note that for d root n, then what you can show is that what this will give you is that actually the 4 norm is less than a constant times the 2 norm. And that is true with or without the 1 over. So that says that, so this actually is why we're hoping for something good, is if I could solve this NP-hard problem, then of minimizing 2 to 4 norm, I could at least figure out whether there's a planted vector. Now, for bigger d, by the way, this is the trade-off that I mentioned about getting 2/3 or something. For bigger d, if I just write the same computation, I get... no. Wow. OK, this is fun. OK, so my... what I end up with, this is the end to the 2/3 that I promised. If I can...
Yeah, maybe it's better to skip it.
Yeah, if I can get back to it. If I can get back to anything on my slides. OK, so... in a second, my slides will recalibrate. But the point was is that what they were showing was that that was just a trade-off that you get at the end of the day. So that the... OK, so there. If we could solve this NP-hard problem, we'd be able to recover, at least determine whether it was a planted vector with a constant. And what are the problems? Really, the problem are just... we can't actually solve NP-hard problems, and it only gives a large inner product, but not exactly the right answer. It just gives a thing that's broad, like got a big inner product. And so the basic picture here is that we're going to now give an algorithm with 2 stages. One of them is going to use the Lasserre sum of squares hierarchy to get an approximate solution, and then the second one will use an LP to recover the exact solution from any solution that's reasonably correlated to it. And OK, so I'm going to focus on the approximate solution. And so what was the idea? The idea is that I'm going to write out a proof of how I would do it for actual legitimate expectations, and then note that my proof works at degree 4. So here's the lemma that this all kind of revolves around. The assertion is that suppose I give you a linear subspace with any kind of with the promise that nothing in it has a 4 to 2 norm bigger than some constant c. And then I also give you a planted vector that has a big 4 norm. And I give you some probability distribution over the span of the 2 that has a big 4 norm. Then the assertion is that the expected inner product of anything sampled from this distribution with my planted vector is pretty big, where pretty big is a ratio of its 4 norm versus the worst case in the other subspace. So why is this true? Well, OK, this is going to be true sort of easily. In fact, let me now throw in one more fact, and it will work for hierarchies too. So let me now, what we're basically going to use for our whole proof is we're going to say, don't just assume that our subspace legitimately doesn't have a vector with bad 2 to 4 norm ratio, but suppose that it has this fact, and it's true with a degree 4 sum of squares proof. Meaning, suppose I give you any subspace where I can actually write a proof of that inequality at whatever, let's say degree 4, although it doesn't really matter. OK, so in that case, my assertion is that you can actually translate this whole statement through to hold for pseudo expectations, right? So the lemma will be true for real probability distributions, and then if I can prove the assumption with low degree, then I can prove the conclusion with only slightly worse degree. And so then this tells us that the actual way to solve the whole problem is to solve a degree 8 relaxation of maximizing the 4 norm subject to the 2 norm, and then what we'll do is we'll prove the lemma for actual distributions, then translate the proof to low degree. So the last part, which is probably the harder part, is just getting a low degree proof of the fact that the 2 to 4 norm ratio of a random subspace is bounded. So let me, I think I only have about 5 minutes left, so I'm going to run through this pretty quickly. The proof of the lemma for actual distributions is super easy. Basically, you write any vector in the span of these two things as your planted vector plus some other junk that's in the original random subspace. And then you just use standard norm inequalities and get that it can't have a big dot product, right? Like this is just a bunch of Holder inequality and Cauchy-Schwarz applications. And something is continuing to go wrong with my sorry, this is what, oh, there we go, full proof. Okay, so the proof for pseudo expectations is basically to write exactly the proof I just did, but do it sort of only using polynomials. And if you look at the proof, sort of the main steps, first of all, I wrote things with fourth roots in them, so I have to undo those. And then the other thing is that I have to somehow I used Cauchy-Schwarz and Holder's inequality. And kind of the main point here was that you actually can write low-degree proofs of Cauchy-Schwarz and Holder's inequality. So the idea is we're building up this proof system of what we can certify at low degree. And these are two facts that any distribution consistent with a 4-norm bound, if that holds, then you can actually just check using positive semi-definiteness. You can just check that actually it will obey Cauchy-Schwarz and Holder. So, okay, so that was the translation to a low degree proof part of it, was we just write the proof for pseudo expectations and then note that all the lemmas we used actually hold under these weaker assumptions.
So this is your rounding, right?
Right, this was our rounding algorithm, actually. So our rounding algorithm is now, that actually is a whole rounding algorithm, other than the fact that I have not proven low degree proofs of the 2 to 4 of the ratio for random subspaces. Right, so what the rounding algorithm is that I've just proven that not only does it hold for the fact that this held for real expectations was easy, and the fact that it held for pseudo expectations is actually only a little harder. It was just kind of carefully writing out the proof with polynomials. And then that says actually that the answer to our SDP, the optimal solution, was a pseudo expectation that actually obeyed these properties, and thus that guaranteed that we actually could pull out a good solution.
So now for random subspace, you need something like eigenvalues of random matrices.
Yeah, it's actually a little, even that, well, morally, yes. You need it, yeah, so I mean, give me one slide for that.
But that part doesn't need to be proven, right? That sort of can be, that's
right.
Outside the system.
Yeah, so the idea is you need to know that the random matrix fact is true. You don't need to, you can prove eigenvalue bounds at degree 2. Right, like so.
Can you say a little bit more? This is the part that always confuses me. Why don't you need a proof for that?
Yeah, so let me put the proof sketch up for that, and then I'll point at it to answer it.
Plug in the degree 4 sum of squares proof for this fact about the subspace.
I think his question was, why don't you need to? So,
Yeah.
If you were to solve for the best
Sorry?
solution, I mean, this will guarantee that if you were to find the proof numerically, then you would find it.
But maybe it'll be clear
Okay.
after this line.
yeah, it should be clear in a sec, but the short answer is just if I gave you a matrix that I want to certify a bound on its biggest eigenvalue, then I can just, I can do at degree 2 by adding the square of something to it to make the identity.
I see. Okay, right.
But it's a subtle point that kind of is, okay, so let me just very quickly tell you that proof is probably the last thing I'll get to, is what is the degree 4 proof? So what's left over from this was that we have to give a low degree proof that a random subspace actually doesn't have a sparse vector in it. And this is kind of the algorithmic crux here, I think, because the rest of it was pushing around expectations, and it was a nice intuition about how to use pseudo expectations. Here, though, the point is that this is the fact that we're really exploiting. That is a strong fact about random subspaces. It says if I give you a random subspace, it has no vectors with a very bad ratio of 4 to 2. And the way we're going to do it is we're going to show the following. We're going to show that the projection operator, pi onto v prime, so that's the linear projection, that of f to the 4, we're going to show that it equals the 2 norm squared minus the sum of squares. Right? So we're going to give, so remember, and this is sort of the quantifier that Sanjay was asking about, was it's not that we have to write the proof that a random the proof that it's going to involve random matrices. We don't have to write the proof that a random matrix has small eigenvalues. We don't have to write that proof at low degree. We have to say, given a specific random matrix, that we can certify a bound at low degree.
I see. So the math that you can assume without proof is eigenvalues. Because you are in this.
Yeah.
I see.
So
anything about eigenvalues you don't.
Right, actually, so we don't have to be able to, so I guess what I'm saying is we don't have to be able to construct the proof using low degree functions of the input. We just need there to be a low degree proof. Given the input.
But what I'm saying is, if you were using, I don't know, some theorem of algebra, You would need to prove it.
Yeah.
But just eigenvalues is special because it's.
Yeah. Somehow, well, they're special-ish. They're special in their squares. They're special in that an eigenvalue is the answer to an SDP.
That's what I mean.
I mean, like.
I mean,
So if you were to use some other math theorem.
you can use
You
the
can use
existence
whatever
of
you
organic.
want, but I mean, like to prove this thing, whatever you could use whatever you want. I mean,
No, but it has to be low degree then.
no. I mean, for example, it could have been that V prime, instead of being a random subspace, would be a subspace that comes out from number theory.
Yes.
And it could be a very, very deep theorem
Yes.
that there is a degree for SOS proof of this thing, but it uses all kind of crazy math.
No, but all of that has to be
But that
proven
would
in
be
degree
fine.
4.
No, so let me put the proof up, and then I'll point out what it is. But roughly, let me just say what I think they're saying is okay. So the end of the day is I'm given an actual input subspace, and it was generated randomly, but I don't have to know that it was generated randomly. I just give you the subspace. Like I'll give you a basis, and what I have to be able to do is prove for you using any techniques I want that there exists a low degree certificate of this bound for the subspace.
Right.
So I can use anything I want to prove the existence of the certificate, but the certificate has to be simple. And the certificate that is simple is something of this form, right? It's a polynomial equality that says I can write one polynomial as another plus a sum of squares. And so the numbers in that certificate, like the SOS is a polynomial, the coefficients of that polynomial don't have to be low degree functions of the subspace or anything nice like that. It just has to be that there exists a certificate, and I can, so that the certificate is low degree. So that's, I guess, in the eigenvalue picture, the same thing could be said, right?
But eigenvalue, it goes without saying. Regardless of what deep number theory you use to prove the eigenvalues, you can
Right.
compute them.
Yes, but no, you can't. No, the eigenvalues are not a low degree polynomial of a matrix, right? Like, that's a very good example, right? If I gave you.
So maybe finish
Okay,
this
good.
slide.
So let me finish the slide. So anyway, the upshot is essentially you're showing that for IID Gaussians, you can prove this inequality. If I then gave you so let me just kind of write out what this says. It says that if I gave you the rows of matrix A, these are the polynomials that we have. And if we sort of start writing things out with tensors, just to write out what the actual assertion is, what do we get? We get this n squared by n squared matrix corresponding to a degree 4 polynomial. And we just have to convince ourselves that, so I'm going to brush through the algebra to get to the point. The point is that if we actually manipulate this a bit, what we're really trying to show is that the polynomial we're looking at, it's going to be a sum of rank 1 matrices, which are coming as each of these A sub i's, each of the rows of the matrix, so each row of A becomes an n squared length vector. That sort of, if you were to vectorize this, is AA transpose. And then you're summing up rank 1 matrices from those, the rank 1 matrices generated by each of those. So it's a bunch of rank 1 n squared by n squared matrices. And so now what we're going to do is we're going to use matrix concentration to bound the spectral properties of sums of random rank 1 matrices.
Maybe.
So I just want to get to the last part of it, which was that if you, sorry, I'm having real technical difficulties. The upshot was that if you just were to bound the eigenvalues of this matrix, of the matrix that you write down, it actually wouldn't be enough. The eigenvalues themselves actually aren't that small. But it turns out that you can add, we have this ideal of constraints that the polynomials we're looking at have to obey. And so polynomials on the sphere have L2 norm 1. And if you sort of add stuff where, if you use that constraint, you can kind of manipulate the matrix into one that then does have a good eigenvalue bound. Okay, so just to kind of conclude everything, the upshot of all of this, I ran a little slow, was that what we were going to get this gave us an approximate solution. You can then solve a linear program to turn an approximate one into an exact one. And the kind of main moral picture from the talk was you want to find sparse objects. And if you do L1 versus L infinity bounds, there's a very good reason why they cut off at 1 over root n, which is just that subspaces either tend to or always do have vectors with bad ratios of L1 versus infinity. And so what we can do is replace that with a ratio of other polynomial norms. And the ratio now that we're looking at is the 2 versus 4 norm. This is an NP-hard problem to actually find. But often in many cases, especially revolving around sort of random instances or sort of learning settings, you can actually certify the bound on the optimum, even if you can't actually always find it. And then that certificate is by itself enough to round these SDP solutions. OK, so I think I am 5 minutes over my 5 minutes overtime. And so maybe I will take questions offline. And thanks.